Hello everyone, welcome back. In this lesson, we're going to look at a few more examples of the ANOVA F test, and these examples will be very similar to what you should expect for the final exam. So let's have a look at example 24.2. An experiment to determine the effect of several methods of preparing cultures for use in commercial yogurt was conducted by a food science research group. 3 batches of yogurt were prepared using each of the 3 methods. So we have traditional, ultrafiltration, and reverse osmosis. A trained expert then tasted each of the 9 samples presented in random order and judged them on a scale from 1 to 10. So here we have a partially complete ANOVA table. And so here we have the sum of squares and the p-value of the ANOVA table. So let's first calculate the mean square of the treatments and the mean square of the error. So to find the mean squares, we need to determine the degrees of freedom for both the treatment and the error. So the treatment degrees of freedom is the number of groups minus 1. So here the number of groups is going to be 3. We have 3 different methods that we're testing. So we have 3 minus 1, which gives us 2 degrees of freedom for the treatment. And then to find the error degrees of freedom, we're going to take the total sample size minus the number of groups. So here we have 9 total samples, so 3 from each of the different methods for a total of 9. And we have 3 different groups, so that gives us 9 minus 3, or 6 error degrees of freedom. So now we can fill in the rest of the table as well. We can calculate the total degrees of freedom, which is the sum of the treatment and the error degrees of freedom. So 2 plus 6 gives us 8 degrees of freedom. We can also calculate this by taking the total sample size minus 1. So that is 9 minus 1, which is also 8. So now we can calculate the treatment mean square. So recall that the treatment mean square is the treatment sum of squares over the treatment degrees of freedom. So we're given that the treatment sum of squares is 17.3 and the treatment degrees of freedom is 2. So that is 17.3 divided by 2, which gives us 8.650 for the treatment mean square. And as for the error mean square, we take the error sum of squares and divide it by the error degrees of freedom. So that gives us 0.4060 divided by 6. And this is 0.0766. Okay, so now we can use the mean squares to calculate the F statistic. So the F statistic is the treatment mean square divided by the error mean square. So we have 8.650 divided by 0.0766, and our F statistic is 112.826. Let's fill this in our table as well. And so now we have our complete ANOVA table. All right, so what does the p-value say about the null hypothesis? So we're given that the p-value is 0.000017. All right, so the p-value is the probability of observing our test statistic. So we have an F statistic with 2 numerator degrees of freedom and 6 denominator degrees of freedom, being larger than 112.826. So we're given that this is equal to 0.000017. So what is the interpretation of the p-value? So the p-value says that if the null hypothesis is true, right? Remember that for the null hypothesis of the ANOVA test, we assume that the means of all groups are equal. Then the probability of observing our sample statistic, or more extreme than our observed statistic, is 0.000017. Okay, so we get a very low probability of observing our test statistic. So this tells us that it is very unlikely that we observed our sample data if we assume that the means of all groups are equal. And so this will provide strong evidence to conclude that at least one of the means differs from the group. And so we have very strong evidence against the null hypothesis. Okay, so what assumptions were made in the test? Well, we have the independence assumptions, right? So the judge's score of one method should not affect the judge's score of other methods. So they should be independent of one another. To check for independence, we look for randomization. So we're given that the samples were presented in random order. So the 9 samples were presented in random order, and so this condition is met. We need to assume that the population variances are equal. And we also need to assume that the populations come from a normal distribution. Okay, so now what should be seen in order to justify the conclusions of the F test? So what we should look for is the side-by-side box plots for each group and compare the spreads for checking equal variances. So we want to make sure they have a similar spread. And to assess normality, what we could do is look at the normal probability plot of all the residuals for assessing normality. Okay, recall that a residual is the difference between the observation and their respective mean. So if we plot the residuals all together in a normal probability plot, and if they lie on a straight line, then we can assume that the populations come from a normal distribution. All right. So now, what is the average size of the residual standard deviation in the judge's assessment? So let's have a look at calculating the pooled or residual standard deviation. So recall that when we calculated the error mean square, this was a pooled variance. And we can write this as SP squared, and this is the error mean square. So the residual standard deviation is going to be the square root of the error mean square. And so SP will be the square root of MSE. So recall from our table, the error mean square was 0.076. And so the residual standard deviation is going to be the square root of 0.076. And this will be approximately 0.277. All right, so this is the average standard deviation across all groups. Okay, so now let's have a look at another example. So here we have the weights of poplar trees that were obtained from trees planted in a sandy and dry region. So the trees were given the different treatments. So we have the no treatment, the fertilizer, irrigation, and both fertilizer and irrigation as the 4 different treatments. And we have an incomplete ANOVA table given below. So let's fill in the missing information and then test at a 5% significance level to test the claim that the different treatment categories yield poplar trees with the same mean weight. Okay, so let's have a look at this table here. So we're given some information from the ANOVA test, and we want to determine the missing information. So let's have a look at the degrees of freedom first. So the treatment degrees of freedom, or the between group variability, is the number of groups minus 1. All right, so here we're given 4 different treatment groups, and so we have 4 different groups, which gives us 3 treatment degrees of freedom. Okay, so K minus 1, or 4 minus 1, gives us 3 treatment degrees of freedom. So now we can calculate the error degrees of freedom because we know the total degrees of freedom and the treatment degrees of freedom, right? So we know that the total degrees of freedom is the treatment degrees of freedom plus the error degrees of freedom. So if we use some algebra here and solve for the error degrees of freedom, we take the difference between the total degrees of freedom and the treatment degrees of freedom. So the total degrees of freedom is 23, and we calculated the treatment degrees of freedom to be 3. So this will give us 20 error degrees of freedom. Alright, so now that we have our degrees of freedom, we can use this to calculate the other missing information. So we're given that the treatment mean square is 0.12456, and we also have the treatment degrees of freedom. So now we can use this information to calculate the treatment sum of squares by rearranging a formula for the treatment mean square. So recall that to find the treatment mean square, we took the treatment sum of squares and divided it by the treatment degrees of freedom. So now we can rearrange and solve for the treatment sum of squares. So if we multiply both sides by the treatment degrees of freedom, we get that the treatment sum of squares is the treatment mean square times the treatment degrees of freedom. So the treatment mean square is 0.12456 multiplied by 3 degrees of freedom. This gives us our sum of squares, which is 0.7368. Okay, so we can fill this in our table. So we have 0.0373 68. Okay, so now that we have the treatment sum of squares and the total sum of squares, we can use some algebra to calculate the error sum of squares. So recall that the total sum of squares satisfies this identity. We have the treatment sum of squares plus the error sum of squares. So if we rearrange and solve for the error sum of squares, we take the total sum of squares minus the treatment sum of squares. So we have 4.473 minus 0.37368, which gives us 4.09932. Okay, so now that we have the the error sum of squares and the error degrees of freedom, we can now calculate the error mean square. So the error mean square is the error sum of squares over the error degrees of freedom. So this is 4.09932 divided by 20, and this will be 0.204966. And lastly, we can calculate our F statistic. So our test statistic is going to be the treatment mean square over the error mean square. So we have 0.12456 divided by 0.204966, and our test statistic is 0.6077. And the p-value is going to be the probability that we observe our test statistic with 3 numerator and 20 denominator degrees of freedom being larger than 0.6077. And we're given that this is 0.6177. So now we're testing at a 5% significance level, and our p-value is larger than alpha. And because our p-value is larger than alpha, we will fail to reject the null hypothesis. Okay, so there is insufficient evidence to conclude that at least one of the mean weights of poplar trees differs from the group.